The tiny powerhouses transforming semiconductor technology. We have several ways of describing energy, said Beecham, associate professor of mechanical engineering. When we talk about light, we describe it in terms of particles called photons. Heat also carries energy in predictable ways, and we describe those waves of energy as phonons. But sometimes, depending on the material, photons and phonons will come together and make something new called a polariton. It carries energy in its own W.I., distinct from both photons or phonons. Like photons and phonons, polaritons aren't physical particles you can see or capture. They are more like ways of describing energy exchange as if they were particles. Still fuzzy? How about another analogy? Phonons are like internal combustion vehicles, and photons are like electric vehicles, Beecham said. Polaritons are a Toyota Prius. They are a hybrid of light and heat, and retain some of the properties of both. But they are their own special thing. Polaritons have been used in optical applications, everything from stained glass to home health tests. But their ability to move heat has largely been ignored, because their impact becomes significant only when the size of materials becomes very small. We know that phonons do a majority of the work of transferring heat, said Jacob Minyard, a PhD student in Beecham's lab. The effect of polaritons is only observable at the nanoscale. But we've never needed to address heat transfer at that level until now, because of semiconductors. Semiconductors have become so incredibly small and complex, he continued. People who design and build these chips are discovering that phonons don't efficiently disperse heat at these very small scales. Our paper demonstrates that at those length scales, polaritons can contribute a larger share of thermal conductivity. We in the heat transfer community have been very material-specific in describing the effect of polaritons, said Beecham. Someone will observe it in this material or at that interface. It's all very disparate. Jacob's paper has established that this isn't some random thing. Polaritons begin to dominate the heat transfer on any surface thinner than 10 nanometers. That's twice as big as the transistors on an iPhone 15. Now Beecham gets really fired up. We've basically opened up a whole extra lane on the highway. And the smaller the scales get, the more important this extra lane becomes. As semiconductors continue to shrink, we need to think about designing the traffic flow to take advantage of both lanes, phonons and polaritons. Minyard's paper just scratches the surface of how this can happen practically. The complexity of semiconductors means that there are many opportunities to capitalize upon polariton-friendly designs. There are many materials involved in chip making, from the silicon itself to the dielectrics and metals, Minyard said. The way forward for our research is to understand how these materials can be used to conduct heat more efficiently, recognizing that polaritons provide a whole new lane to move energy. Recognizing this, Beecham and Minyard want to show chip manufacturers how to incorporate these polariton-based nanoscale heat transfer principles right into the physical design of the chip, from the physical materials involved, to the shape and thickness of the layers. While this work is theoretical now, physical experimentation is very much on the horizon, which is why Beecham and Minyard are happy to be at Purdue. The heat transfer community here at Purdue is so robust, Beecham said. We can literally go upstairs and talk to Xianfan Xu, who had one of the first experimental realizations of this effect. Then we can walk over to FlexLab and ask Sholan Ruan about his pioneering work in phonon scattering. And we have the facilities here at Berk Nanotechnology Center to build nanoscale experiments, and use one-of-a-kind measurement tools to confirm our findings. It's really a researcher's dream.